This is lesson number 3 in college algebra. We are still in unit number 1, and we are still talking about an introduction to sets of real numbers and set theory. This is lesson 3, and today we'll be practicing writing in set notation and defining null set and subset. As we're looking at set notation, which is what we discussed last time, that there are several ways to write a set, and in the 3 examples that we have below, this needs to turn into a 3. In these 3 examples we have below, most of these sets are written in set builder notation to give us some idea of how to decode some of the symbols for set notation. So we'll take a look at this. Determine which equivalent sets in the following groups, which are equivalent sets in the following groups of sets. So which of the following sets are equal to the set of all integers that are multiples of 5? There may be more than one. So here we have written the set of 5n such that n is an element of R. Number 2 says the set of 5n such that n is an element of Z. Number 3, the set of n an element of z or integers such that n is equal to 5k, and k is also an element of the integers. Number 4 reads the set of n an element of z or integers such that n is equal to 5k and n is equal to an element of the integers. And then for number 5 we just have -5, 0, 5, and 10. So we want to know which of these is equivalent to all the sets of integers that are multiples of 5. So I would assert that 2, 3, and 4 follow the are equivalent sets to this set. It follows the conditions, the set of all integers that are multiples of 5. Why not number 1? First of all, 5 is being multiplied by n, and n is any real number. So since n is not defined as an integer, that would not work. And then for number 5, we only have a selected group of multiples of 5. So we only have 4 elements in this set, and it asks for the set of all integers that are multiples of 5. Number 2 reads that 5 is being multiplied by all the integers, because n is an element of the integers. So number 2 checks out. Number 3 checks out because n is an integer and it's being multiplied by all the integers, which are defined as k. So this one checks out. And number 4 also checks out because k necessarily has to be an integer if n is also defined as integers. And here we define it twice, which is redundant, but it still works. Number 2 reads, which of the following sets are equal to the set of all negative real numbers? And there may be more than one or none. So we're looking for which of the following sets given in symbolic notation is equivalent to the set of all negative real numbers. Okay, I would assert that this follows number 1, number 3, and number 4. Excuse me, number 4 would not work because this appears to be the set of only integers. Okay, so that would not work. Number 2 does not work because this is also only the set of integers. But number 1 and 3 includes all real numbers. Number 1 reads, the set of all n such that n is an element of the real numbers and n is less than 0. So that would be all the negative real numbers. Number 3 is written in interval notation, which includes all the real numbers from -infinity to 0. So that would be all of the negative real numbers. So for this one, again, we only have 1 and 3. Number 3 reads, which of the following sets are equivalent to the set of all positive integers? There may be more than one or none. I would assert here that 1, 2, and 4 fulfill this set of all positive integers. Let's take a look at it. First of all, number 1 says the set of all n such that n is an element of the natural numbers. Well, the natural numbers are all of the positive integers. Number 2 reads the set of n such that n is an element of the integers and n is greater than 0. So that would be all of the positive integers. Number 3 includes more than just integers. So this is all real numbers. When it's written in interval notation, all of the real numbers are included. So since it's not limited to just the integers, this is not equivalent to the set that is described above. Number 4 starts with 1 and starts listing the counting numbers to infinity. That's the ellipses indicate that this is going to keep going. So this would be all the positive integers. Number 5 says the set of all n such that n is an element of the integers. Well, this includes all the negative integers as well. And so that would not fulfill the conditions indicated by the problem. All right, there's 2 more concepts that we want to understand before we move forward in performing operations on the integer or on sets. And the first one is null set. Null set occurs when there are no elements in the set. It's usually indicated or denoted by this symbol of a 0 with a slash through it, or it can be indicated by a set of braces with nothing inside. It's also known as the empty set. I do want you to be careful though, because null set does not equal 0. Okay? 0 is actually a real number, and so it would not be the equivalent to an empty set. So if there were no solution, or if it were an empty set, then you could not put 0. That would be incorrect. And then the next concept we want to talk about is subset. Subset is a set. Let's define it as A. If we have a subset A of another set, let's call it B, okay, it would be a subset if and only if every element of A is also an element of B. And the symbols denoting this look like kind of a elongated C. So we're saying that A is a subset of B, and this is the symbol denoting subset. All right, so let's take a look at some possible examples and practice writing these sets. So given the set S, this is written in set builder notation, X such that X is an element of 2n, for n an element of Z. All right, so basically I'm taking all of the elements, all right, and I am saying that the elements of S are equivalent to every integer being multiplied by 2. every integer being multiplied by 2. So I want all the integers, multiply them by 2, and that is the set of S. So if I were to write this by listing the elements of the set, okay, I also want negative numbers, so I could start maybe -2, 0, 2, 4, ... indicating that this is an infinite set on either side. So it appears as though I'm just taking the multiples of 2. Another way of saying the multiples of 2 would be all even integers. Okay, now I want to take a look at the set and write 2 subsets of this set. So my set is defined as S, so let's define another set T and make it such that T is a subset of the elements of set S, or a subset of S. In other words, it's a few of the even integers. So we could say 2, 4. Therefore, we could assert that T is a subset of S. So if we were to write this as a Venn diagram, S would be our main set, and we could say that T fits inside. Okay, this asks for 2 subsets, so let's write another subset. Let's call it Q. And we're going to write some elements of the set S. How about -2, 0, 6, 100, 102. Okay, all of the elements of Q are also elements of S, which is the set of all even integers. So we could assert then that Q is a subset of S. In our Venn diagram, since none of the integers are shared with T, we could make Q another small bubble inside of our Venn diagram S. Okay, in this next section, what we want to do is perform some operations on the sets. We're going to perform 2 main operations, namely union and intersection. Let's define union. The union of set A, denoted by A, and then this symbol of a kind of strange looking U, reads A union B. It's the set consisting of all elements that belong to A or B. So in symbols, we would say A union B, like so. Now, this would be indicated through a Venn diagram by saying all of the elements of A united with all of the elements of B. If A were the elements 1, 2, 3, 4, and 5, and B were 4, 5, 6, 7, 8, 9, and 10, okay, it would appear as though they share 4 and 5, so that would go in the middle. 1, 2, and 3 go in A. 6, 7, 8, 9, and 10 go in B. So A union B would then be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. The intersection of sets A and B, denoted by A intersect B or intersection B, this is an upside down, strange looking U, is the set consisting of all the elements that belong to both A and B. So in symbolic notation, we say A intersect B. So in other words, we only want the elements that they share. In other words, we only want the spot where they intersect in the Venn diagram. So again, if we have the elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for A and B respectively, they share the elements 4 and 5. And so A intersect B is equal to the set 4, 5. Next time we will talk about disjoint sets, and we will also be practicing with performing operations on sets.